A coding agent can look magical for a strange reason. You ask it to fix a bug, and a few minutes later, files have changed, tests have run, error messages have been read, and the agent is trying again. But the language model is not secretly living inside your computer. The model is mostly choosing the next action. The surrounding program is what actually reads files, edits code, runs commands, stores history, and decides what information goes back into the model. That surrounding program is the harness. PyAgent is interesting because it is often discussed as a small, concrete example of this harness idea. It helps us see why a coding agent is not just a chatbot with a bigger text box. A chatbot mainly replies with words. A coding agent runs a loop. The model decides. A tool executes. The result returns. The context updates. Then the model decides again. Once you understand that loop, tools like Claude Code, Codex, Cursor, and similar coding agents become much easier to reason about. The first misconception to clear up is simple. The model does not directly open your editor and type into your project like a ghost. In most agent systems, the model receives a description of tools it is allowed to use. A tool might be read a file, search a folder, edit a file, run a shell command, or report the current working directory. The model responds with a special tool request. The harness reads that request, checks whether it is allowed, runs the real operation in your environment, captures the result, and feeds that result back into the next model call. Think of the model as the planner sitting at a desk and the harness as the assistant with access to the building. The planner can say, "Please inspect this file," or run the test command, but the assistant is the one who actually walks down the hall and brings back the result. In a tiny coding agent, this separation is easier to see because the parts are not hidden under layers of product polish. Py-style agents usually emphasize a small set of powerful tools rather than dozens of custom buttons. If the model can read files, write files, apply edits, and run bash commands, it already has access to most of what a developer uses every day. It can inspect package files, run tests, search with command line tools, call Git, format code, and read compiler errors. This is why a very small agent can feel surprisingly capable. The hidden power is not a huge menu of tools. The hidden power is that the terminal is already a universal toolbox. Now let us walk through one simple task. Imagine you ask the agent to fix a failing login test. The agent starts with your instruction and some system guidance. It may not know where the login code is, so its first decision might be to search the project. It requests a search command. The harness runs it and returns matching file names. The model sees the result and chooses to read a test file. The harness opens the file and returns its contents. The model notices that the test expects one error message, but the implementation returns another. It asks to read the implementation. The harness returns that code. The model proposes a small edit. The harness applies the patch. Then the model asks to run the relevant test. The harness runs the command and returns the output. If the test passes, the model summarizes the change. If it fails, the output becomes the next clue, and the loop continues. This is the basic engine of agentic coding. Not one giant answer, but repeated observation and action. The terminal user interface matters because it makes this loop visible to the human. In a normal chat window, you might only see a final message and maybe a block of code. In a coding agent interface, you often see tool calls, file diffs, command outputs, approvals, and status updates as the work unfolds. That is not just decoration, it is part of trust. If an agent says it fixed your project, you need to know what it touched. Did it change one file or 20? Did it run the test suite or only guess? Did it delete something? Did it create a new dependency? A good harness shows enough of the process that the human can supervise without reading every token. A tiny agent also reveals an important design trade-off. If you give the model a bash tool, you give it enormous reach. It can run tests, install packages, inspect Git history, start servers, and use existing developer tools. But that same power creates risk. A bad command can delete files, leak secrets, or change your machine in ways you did not expect. That is why harnesses usually need permissions, approval modes, allow lists, sandboxes, or at least a clear preview before risky actions. The model may suggest an action, but the harness should decide how much freedom it gets. This is where agent design becomes less like writing prompts and more like building a safe operating environment. If this explanation is making the machinery clearer, consider subscribing. The goal of this channel is to make AI and future technology feel less like magic and more like systems you can actually understand. The next layer is context. A coding agent has to remember the conversation, the files it has read, the commands it has run, and the decisions it has already made. But models have limited context windows. Even large windows eventually fill up during long sessions. If the harness keeps sending every file, every command output, and every message forever, the session becomes expensive, slow, and noisy. So the harness needs context management. It chooses what to include in each model call. It may keep the latest user request, the current plan, relevant file snippets, recent tool results, and a summary of older steps. This is one reason two agents using the same model can behave very differently. The model may be identical, but the harness may feed it different memories. Compaction is a key part of this. Compaction means the agent takes a long history and compresses it into a shorter working summary. Imagine a notebook that starts with every detail of a repair job. After a while, you rewrite the important parts onto one page. The broken test is in this file. We already tried this approach. The current theory is that the error comes from this function. The branch has these edits. That summary lets the session continue without carrying every old log line. But compaction is not perfect. If it leaves out the wrong detail, the agent can repeat a failed idea, forget a constraint, or misunderstand why a change was made. This is why long-running agents can drift. The problem is not only model intelligence, it is memory hygiene. Sessions are another hidden mechanism. A session is not just a chat transcript. It is a record of the evolving workspace relationship between the user, the model, the tools, and the project. Some agents save sessions so you can resume later. Some let you fork from an earlier point, which is like saying, go back to the moment before we chose this approach and try another path. That matters because coding is exploratory. You often do not know whether a refactor is correct until you run it. A session system lets the agent preserve the trail of what happened, while still giving the human ways to recover, compare, or restart. File edits are also more subtle than they look. A weak agent might output an entire file and hope the replacement works. A better harness can support targeted edits, patches, or diffs. This reduces accidental damage and makes review easier. The model still has to understand the code, but the harness can shape the edit operation so it is safer and more auditable. When you see a diff, you are seeing the agent action translated into a format developers already trust. That is another important point. Good coding agents do not replace software development practices. They plug into them. Tests, diffs, version control, linters, type checkers, and code review become feedback channels for the loop. Skills are another piece of the puzzle. A skill is usually a reusable instruction or capability for a specific kind of task. Instead of stuffing every possible rule into the main prompt, the harness can load extra guidance only when needed. For example, a project might have a skill for writing database migrations, another for using a company test framework, and another for preparing pull request descriptions. This is like giving the agent a small manual at the moment it needs it, instead of forcing it to carry the whole library all day. The advantage is cleaner context. The risk is that the agent may load the wrong skill, miss a needed one, or follow outdated instructions. Again, the harness matters. It decides how skills are found, loaded, updated, and trusted. This leads to the biggest misunderstanding about coding agents. People often ask which model is best, as if the answer explains the whole product. The model matters a lot. Better reasoning and better code understanding help. But the agent is the model plus the harness, plus the tools, plus the environment, plus the feedback loop. A strong model in a poor harness can behave like a brilliant person trapped in a room with no files, no terminal, and a messy memory. A smaller model in a clean harness can sometimes do useful work because it is given the right observations and narrow actions. The quality of the loop determines whether mistakes are caught or amplified. There is also a practical consequence for users. When a coding agent fails, do not only think the AI is dumb. Ask where the loop broke. Did it have enough context? Did it read the right files? Did it run the right command? Did the test output get summarized badly? Did it have permission to inspect the dependency it needed? Did it edit too much at once? These questions turn agent failures into debuggable system failures. That is a healthier way to use the tool. You are not begging a chatbot to be smarter. You are supervising an automated worker that observes, acts, and reports back through a harness. PyAgent is useful as an example because its smallness makes the architecture easier to see. Strip away the branding, and the core idea is surprisingly simple. A coding agent is a loop wrapped around a language model. The loop gives the model tools. The tools touch the real project. The results become new context. The session keeps track of the journey. Compaction keeps the memory small enough to continue. Skills add task-specific knowledge. Permissions and interfaces keep the human in control. That is why coding agents feel different from autocomplete. Autocomplete predicts the next piece of code while you are already editing. An agent can inspect the project, choose steps, make changes, run checks, and revise its plan. It is still fallible. It can misunderstand requirements, over-edit files, ignore edge cases, or pass tests for the wrong reason. but it is operating in a richer loop than a text box. The payoff is that once you see the harness, you can evaluate any coding agent more clearly. Do not only ask whether the demo looked impressive. Ask what tools it can use, how it asks permission, how it shows diffs, how it manages context, how it runs tests, how it stores sessions, how it handles long tasks, and how easy it is to recover when it goes wrong. The future of coding agents is not just bigger models answering longer prompts. It is better loops around models. If you have a question about coding agents, Pi-style architecture, or the difference between tools like Claude Code, Codex, and Cursor, leave it in the comments. And if there is another AI system you want explained from the inside out, suggest the next topic.